the French and the German methods. The French being Lagrange, the German being, the French and the Irish. We'll get to the German one much later, which is Riemann equations. Okay, now, these are the invariants, things that don't change when you're riding on all of these gadgets. And that is, I think, really important. And the first one that doesn't change, and this is kind of neat, the area of a triangle made by r and velocity, that is r cross v over 2. The area of that dark blue triangle there. Or a rectangle that's made out of the two hypotenuse to hypotenuse. That's a rectangle, but most of the time it's a parallelogram, or a fat rectangle, or a parallelogram rhombus, pointing whatever you want to name the geometry that indicates what a particular time. So just to see that, that's something you can do very easily if we know what the position and velocity components are. I'm just taking what we've already written down for the velocity on the isotropic oscillator elliptical orbit. And that works out the nice big constant. AB, the major axis of the orbit times the minor axis and the frequency. That's kind of a nice thing to know. Now the angular momentum of this thing, this is the definition of it. That's something we'll be deriving more elegantly. R cross V, but something you already know from sophomore physics. Those quantities, let's just stay a little bit quiet here. R cross V, remember that is the product of this and this and the sine of the angle. That gives you an area of that particular figure there. And the idea is that all of these quantities, area of the triangle, angular momentum, and the area swept, that's what we're calculating right here, that is changing, but it's changing linearly with time. So wherever you started and in a later time, you have here an integral of r cross v over 2. Well, r cross v over 2 is a big fat constant, and so you put that in and bingo, you just have the angular momentum times the time. Now what's interesting about all of these is this isn't just the oscillator that does this. This is something that's true for all central force, that is isotropic force laws. Take any force law that you can make isotropic, and this will be satisfied. These are constants of the motion. Okay. And let's see if there's anything else I need to say here that's worth. Basically, what this is saying is in one period, this thing for the ellipse orbit works out to be this area on the ellipse. That's just the area of the ellipse, AB times pi r squared, but now r squared is replaced by a times b, the two radii products. Okay, let's see if there's, if you stick in the formulas we've already derived from the sophomore Earth discussion, putting in the constant, that's back in lecture 6. So that is what's at the bottom of this particular thing. Let me keep this one going as well. Okay, now the next thing I want to show here that has to do with this is the use of the angular momentum invariance and also the energy invariance in these objects of motion here. The having this area be a triangle. Now, as I say, in Unit 5, we do the Coulomb. Coulomb requires just a little bit more finesse than I want to have at this particular moment. But for this one, this area of a triangle, A times B, and then here are the actual MKS constants. that go for the sophomore physics Earth, that is definitely a nice formula to have. This one is just a little bit different. It's got the inverse square root instead of just a, and we'll be deriving that later on. And let me put that up on the screen down there. And the next thing, angular momentum is being conserved here. That quantity that we just took and then took from the lecture 6, that has the MKS values. This here depends on the total mass. You're outside of the Earth now for the Coulomb orbits. Inside the Earth, you use the density, the square root of the density as a coefficient for the angular momentum. Okay, this one you use the mass of whatever it is you're orbiting to calculate the orbital angular momentum L. Okay, so that's worth noting. And then the area swept. This is kind of neat as well. Area swept, comparing again what we've just derived for the isotropic oscillator to what's coming for the Coulomb orbits. Now this is kind of interesting here because you'll notice that the B cancels, but you don't get, well, here the AB cancels because what we're talking about is measuring of a period. Let me carry that completely out. There's cancellation marks. Okay, so for this guy right here, the time for one period is totally independent of the shape of the ellipse, no matter where you throw something, whether it's on a straight line in this classroom with a perfectly straight plane, or whether you're actually going all the way through the Earth without friction, as a neutron star might do, and have no function of A and B at all. But for the Coulomb orbit, it does have a function of just A, not a function of B. So that's worth noting. Now we've got energy to talk about yet, but this is the angular momentum and the timing. Both of those are related very closely, and you can see the difference between these two in the sense of this one being a constant and that one being dependent on only the major axis. Well, it turns out energy does that too, as we'll see in the next go here. So let me move ahead to that. This is kinetic energy plus potential energy, the total energy. And now, here's what I want to spend some time today just getting a start on, and that is, these are quadratic forms. So with an oscillator, that's the potential energy. There's the very simple diagonal and unit, basically, product of unit matrix. Same with a mass. Okay, so these are really simple quadratic forms, but the idea is what I'm trying to generalize this idea a little bit here. In any case, when you add up all of the various pieces, given what we know for position and velocity, it becomes very simple. That is, it becomes a constant depending on A and B. And it's A squared plus B squared with the omega squared. So that I point out here right now. Okay, so question is, what does Coulomb do? Just for curiosity's sake, that's worth noting. This particular frequency of the period, not a function of V or A, but for Coulomb orbits, as we'll see, that adds up to this particular thing. That is, it adds up to something that is just a function of A. The major axis determines the period and the total energy for the here, no constant. no A and B involved at all. Okay, so that's that. Okay, now the rest of this lecture today is somewhat mathematical, in the sense I want to make clear the geometrical structure that lies behind a quadratic form, but just what lies behind when you use a matrix to move a vector. Where does it go? That's the first order of business here, which we definitely want to get through. Whether we have time for some of the more intricate things of this is, remains to be seen. In any case, all of this stuff is in the text, but I'm trying to present it more, shall we say, clearly, that is, step by step. When we say we generate an ellipse with a quadratic form, well, we just have some kind of matrix here, and then we have R, the vector R on both sides here. And what you're doing, of course, when you work this scalar product out, is get the equation for an ellipse. That's assuming A and B are real values of a radius of a major and minor part of an ellipse. Now the inverse matrix also has a quadratic form that instead of having the a squared and b squared in the denominator, it has a numerator for whatever variable p is. And p has some connection to momentum, but not quite in this particular stuff that we're doing here. That will come in the next lectures. But I just wanted to make sure we see that these are two different equations for an ellipse, and that the quadratic form, or its inverse, is taking you from R to P or from P to R. Now, how does that work? What's actually happening when you do that transform from R to P? Okay, so here is an ellipse right here. There is R. Well, it turns out there's this little square right here, and basically what you do somehow is Q takes R up to P on another ellipse, the ellipse that goes with the inverse of the quadratic form. That is this guy right here. So there are two ellipses here, one for the original one and the other one for the Q inverse ellipse. So it's a transformation from being here to being there. And the idea is, and that's what we're going to see with this geometry, is a tangent to this ellipse is exactly perpendicular to the vector that you get by doing this transformation. So that geometry I want you to get into your mind as close as we can here. So there are a number of ways to write all of this. Just going through and working out the whatever scale factor. I can rescale this factor, rescale this other ellipse. It's has different dimensions than the original ellipse if this is actually a physical transformation of some kind. And so that would scale it up and make it, well, we'll see what it is here. The main thing that I want to show is this duality that exists between the thing that involves the position, say R, and then this other quantity P, and the basic idea being, first of all, that the dot product of those two is always unit, and the second one is that there's this orthogonality between this and the tangent to this one, and vice versa. So that's the main thing that I'm trying to derive here and make as clear as possible. So this is a picture of that. And here is the actual tangent, the r dot, for the particular position. There's r dot where it would be if you base it in the center. You have a parallelogram here involving the r here and the r dot there. And then t has the same thing. If there was a time associated with orbiting on this, if this were an orbit, and that's why I'm using this. But the main thing to point out here is that the perpendicular p dot, the time derivative, is 0, and the reverse is as well true. P dot, there would be a tangent there, would be orthogonal to that. So that's the duality. P dot vector is right here. It makes a triangle here that has this particular guy perpendicular to, let's see if I've got that right. Yeah, here it is. Here's the P dot, perpendicular to the original position vector. So this is all of the stuff having to do with the quadratic forms, and this is the geometry that connects Lagrangian to Hamiltonian. That's what we're getting at, among other things here. Okay, let's see if there's anything here. And this is where we showed this thing already, but this is the r and the p vectors, and this, I presume, will give this. Maybe they're flipped and we'll get the original one instead. Let's see what happens here. Yeah, no, this is working. There are the r's and the p's doing their little dance, each one of them around. One of them, if it were a Hamiltonian, would be the p, and the other one is associated with Lagrangian actual position and velocity connection with it. So that's just kind of a pretty relationship between these. And there's, I don't have to pause it because it's a static until you move it thing. Okay. Go ahead here real quick. This zigzag construction, where I start with something of an arbitrary slope, I have to pick 45 degrees, but I've got an ellipse, and I've got another ellipse that I get by drawing the rectangles the other way. That's the connection between the r and the p ellipse, and this can be continued. Once I've got a particular point on their respective ellipses, draw another vector to that, and that's going to have slope b over a. That's the effect of taking a matrix and multiplying it by a vector, is to get something that has a slope that is a ratio of the parameters in the ellipse. And similarly for this one, that's the inverse operating on that same vector x and y. And then once we've got the thing over here, I say, well, do it again, do a zigzag again, make another shoe heel there, and while you're at it, you might as well do one up there. And of course, it's pretty easy to show that now you've got something that's a slope ratio squared, and so forth, as I do this more and more time. Now this is the action right here, the action of this square root matrix, the square root of the quadratic form. That's the sort of operation I need to get to the Lagrangian, that's halfway between the Lagrangian and the Hamiltonian. Literally halfway, half power away between them. Okay? So the resulting vector slope has changed by factor b over a after you've done this twice, but just doing it once is a very important operation. Diagonal r minus 1 matrix acting on the vector, whatever vector x and y, is going to be accomplished by that zigzag. Now as you keep doing this, getting higher and higher powers, or lower and lower, actually, slope, because a is bigger than b, but up here it's the reverse. You're getting higher and higher slopes. Basically, multiplying matrix over and over again is a famous technique that's used to find eigenvectors. Okay, in particular the largest eigenvector or the smallest, depending on which one of these you use. Okay, so at some point I've got a vector right here that's immune to either one of these matrices. So that's a cool thing to be aware of, and that's what's at work here. Once you see what a matrix does to a vector, and this is just with 2 dimensions, but you can pull the same stunt in 3. It gets difficult to visualize in 4, but basically the same stuff is happening in higher dimensions. Okay. Rescale it becomes a little clearer how things are working. I rescaled it so I can fit the ellipse inside there. That's sometimes a nice thing to do. And once you've done that, then you can follow the various transformations. Now this stuff is all explained in the text, and it's stuff that helps understand what's coming in chapter 12, but not a whole lot. It's not something that I would rather you look at the very simplest discussions of this. The idea that r dot is perpendicular to P, and that being proved by calculus. That is, the Q inverse map also is part of the story here. Now, if you have a general quadratic form, that's an equation for an ellipse that's at some angle. Okay, so everything we've done can be done at an angle, that's pretty clear. But doing it algebraically, that means you're going to have off-diagonal components in these, not just A and D. And so when you do that, then you're going to be taking a spatial derivative of a quadratic form, and later a velocity derivative of the quadratic kinetic energy form. Okay, those will be all part of the story. And you'll be doing it in 3 dimensions when we actually talk about rotating bodies and all that, which there is one of them sitting right there that will be interesting later on. But in any case, this gradient, the gradient of QR squared, basically, the derivative with respect to the position of r squared would be 2 times r. That is, you reduce the power by 1. Doing it in all out to see what it really does, and the result is, indeed, if you do 1/2, the gradient of 1/2, which is what we had when we write our things 1/2 mv squared and 1/2 kx squared, well, that's really what that quadratic form is in both cases for our oscillator. Okay, so the sequences that you get by playing with that are nice and interesting. I mean, there's all kinds of funny things going on here. The geometry is really quite beautiful in the sense that the tangent cuts at the perpendicular point in each of those transformations. But where we're headed is this. This is what we're after. Our Q, which is r squared, is going to be the mass quadratic form. And then the square root of the mass quadratic form, okay, that's just plain old r. R for root. Well, this is the one that uses the root that makes this guy, which we've seen already, but just want you to see the connection between our Lagrangian that we use for all the superball collisions, with a collision line and a bisector at 45 degrees, becomes this when you just go halfway to the Hamiltonian, where you go all the way where the collision line has a 45 degree, that is minus 45 degree slope. Okay. So it's this, the geometry that underlies all of classical mechanics, and classical mechanics connected to quantum mechanics. The geometry is still there and worth paying attention to. Okay, there's that connection that we need to derive and understand, and we'll be getting to that next week. Okay, we managed to get all that stuff in in a short time, but there we are.